Hello, my name is Chandra Bellasio. In this video I'm showing how to derive a consistent set of C4 photosynthetic parameters starting from combined gas exchange and fluorescence data using the C4 Excel fitting tool. In the first sheet called raw data are entered. Here we have two tables. The first one is for light curves and the second one is for ACI curves, and in particular we can enter here the light curve measured under ambient oxygen and the light curve measured under low oxygen, and similarly we can enter the ACI curve measured under ambient oxygen and the ACI curve measured under low oxygen here. Alongside each data point, it is required to specify a limitation. So here I specified 1 for the initial part of the light curve, 2 for the light limited part of the light curves, and you may specify 3 for the remainder of the points. Since light curves were measured under a maximum light intensity of 1200, there is no really any data point which is not light limited. For the ACI curves, 1 is specified for the initial part of the ACI curve, 2 for the Pepsi limited part of the ACI curve, 2.5 is specified to exclude intermediate data points, and 3 is specified for the light limited part of the ACI curve. To exclude final data points, a limitation, a number higher than 3 may be specified here. The curves are automatically plotted below the table. In blue we have the low oxygen data points, and in brown the ambient oxygen data points. So these are the two light curves and these are the two ACI curves. Sheet 2 calculates respiration in the light according to the method of Yin. The initial part of the light curves measured under ambient and low oxygen is automatically copied in these two tables here. The net assimilation is plotted against this quantity here, 1/3 Y2 ppfd, and the data are fitted to a linear regression. The y-intercept of the linear regression is respiration in the light. Nothing needs to be done here, everything is automatic. We just need to make sure that the regressions are linear. In the standard features, Y2LL, which is the initial yield of photosystem 2 extrapolated under 0 ppfd, is extrapolated linearly. Y2LL is calculated by fitting the initial part of the light curves. In additional features, we may specify a value for dark respiration in cell Z8 and Z9 for low and ambient oxygen. So for example, if we specified 1.5, the value for dark respiration will be automatically plotted in the graph, and the linear curve fitting will include the value for respiration in the dark. Another additional feature allows to fit a value for respiration in the light concurrently to the ambient oxygen and low oxygen light curve. To do so, we may insert a dummy number here, and we may use solver to find the value for respiration in the light fitted, which concurrently satisfies the two curves. The objective cell is cell 13, which is the sum of the square residuals of the two regression under ambient and low oxygen, and the variable cell is Z12. We may solve, and the value found now concurrently fits the two curves. This value for respiration in the light can be automatically copied in the next sheets when respiration in the light fitted is specified. In this table here, we can calculate the light compensation point linearly as an alternative to what we will see later. And finally, here we have three different types of regression to extrapolate Y2LL. Y2LL may be extrapolated with quadratic or exponential regression. We can specify the data to include. If we just type 1, only the initial part of the light curve will be included. If we type 2, the light limited part will be included, and if we type 3, the whole light curve will be included. Since we didn't specify 3 for any data point, there is no change between 2 and 3. Sheet 4 fits a non-rectangular hyperbola to the light curve. The light curve is automatically copied in this light region. If more space is needed in the table, we may follow this procedure. We need to unhide the rank order, move the last row down, and then autofill to complete. We may then complete the table and hide the rank order again. We may not be happy with the copied values, and we may want to change individual data points. The cells with the light colored background can always be overwritten. So in this case, for example, we may copy and paste values. Now, these cells do not contain any formula which links them to the raw data. They are completely independent, and we may modify them or change individual values. So, for example, if you want to delete the last data point, this will not affect any subsequent sheet. In cell G2, it is specified what respiration in the light to use. We may specify, for instance, ambient. And then in G4, one may specify whether to log transform the residuals. The non-rectangular hyperbola has got three parameters. One is the initial slope, which is called the initial quantum yields for CO2 fixation. The second is the horizontal asymptote, which is the light saturated rate of gross assimilation, and one is an empirical curvature of the hyperbola. To fit these parameters, we can go to Data, Open Solver, specify as an objective cell the sum of squared residuals, insert the three parameters as variable cells, and these constraints are meant to speed up the fitting procedure. We may now click Solve. Now the hyperbola represents our light curve. In additional features, we can specify whether to use a value for respiration in the dark. If we insert a number here in Z12, the value of respiration in the dark is automatically plotted together with the light curve. If respiration in the light was not fitted in sheet 2, we may use this curve fitting procedure to fit a value for respiration in the light. To do so, we just insert a dummy number here, and then we may ask Solver to fit cell G2 as well. So now we have a fitted value for respiration in the light. Sheet 4b is identical to sheet 4a, apart from the fact that here low oxygen light curves are modeled. The additional features are the same and allow you to specify a value for respiration in the dark. Sheet 5a fits a non-rectangular hyperbola, analogous to what we have seen in sheet 4, to the ACI curve. Here, 4 parameters are fitted at the same time. Carboxylating efficiency, which is the initial slope of the hyperbola, the CO2 saturated rate of net assimilation, omega, which is an empirical curvature, and the empirical CO2 compensation point. We may specify whether to log transform residuals and what value of respiration in the light we may use. This may include a number or any of the fitted values found before. We may open Solver, set the objective cell as the sum of the square residuals, cell M6, specify the variable cells, cell M2 to M5, and then add a few additional constraints to speed up the fitting procedure. We may click now Solve, and the fitted values now represent the ACI curve. In the additional features, we can evaluate stomatal limitation. The procedure is analogous to the graphical method, apart from the fact that here we are using the fitted hyperbola to find the values for assimilation under the different CO2 concentration. The first value for assimilation is calculated under external CO2 concentration. The second value for assimilation is calculated at the CI, which is corresponding to the external CO2 concentration in operational condition. This may be derived in a separate experiment, or it can be derived from the data of the ACI curve. If it is derived in a separate experiment, the value of Ci may be entered here, for instance 100. In that case we have to delete the rank number. So here we have the modeled value for assimilation under 400 Ca and the modeled value for assimilation under 100 and the stomata limitation. If Ci is derived in the same ACI curves, we may specify the number of data points corresponding to the desired Ci. The ranked number of data points is displayed in column B. So if we know that the value corresponding to the external Ca is the 8th, we may just specify 8 here, and then Ci is automatically copied. Sheet 5b is identical to sheet 5a, apart from the fact that here data measured under low oxygen are copied. The additional features are also the same. Sheet 6 calculates the light conversion efficiency parameters according to yin. These are S prime, which is a calibration coefficient which allows later to calculate JATP, and YJATP-LL, which is the initial quantum yield for ATP production extrapolated under zero light intensity. The derivation is completely automatic, just we need to check that the plot is linear. Additional features allow to specify the value for X, which is used in the calculation of YJATP-LL, and what regression is used to calculate Y2LL, which is also used in the calculation of YJATP-LL. Additionally, there is the possibility to linearly derive YCO2LL in alternative to what we have seen in sheet 4a and 4b. Sheet 6b7 calculates the light conversion efficiency parameters in analogy to the derivation of Valentini. Briefly, YCO2 is plotted against Y2 and a linear regression is fitted. Here we can specify a few things: what respiration in the light to use, what data to include, if just data from the light curve, data from the ACI curve, or both datasets. And then finally we can specify whether to include only the light limited data or not. For example, if we specify not, all data points of both curves are included automatically in the plot. If we specify yes, just the light limited data points are included. The derivation is completely automatic. We just need to check that the plot is linear. Additional features allow to specify what regression to use to calculate Y2LL, which is used in the derivation of YJATP-LL, and what is the value of ATP per GA under low oxygen. Generally 5 is used, but one may specify another value. Sheet 8.9 first calculates a value for JATP at each light intensity, then fits a non-rectangular hyperbola to the light response of JATP. So to use this sheet, first we have to specify how to calculate JATP. Three calibrations are available: Yin, Valentini and Bellasio calibration. When Yin is selected, Excel asks us to specify X. Generally the value of 0.4 is used. When Valentini is selected, Excel asks us to specify ATP per GA under low oxygen. Generally the value of 5 is used. And when Bellasio is used, Excel asks us whether to use the Yin or the Valentini YJATP-LL. Then we may specify whether to log transform reciprocals. We may now fit the curve. The curve has got an initial slope YJATP-LL, which is automatically copied from the selected fitting. A saturated value JATP sat, which is the horizontal asymptote or the value of JATP extrapolated under infinite light intensity, and an empirical curvature of the hyperbola. We may open Solver, select the objective cell M4, which is the sum of the squared residuals, specify the two values of JATP sat and theta as variable cells, a few constraints over theta to speed up the fitting procedure. We may now click Solve. So now the fitted hyperbola represents the PPFD response of JATP. Sheet 10 uses the ATP limited model of C4 photosynthesis to fit a value for bundle sheet conductance to CO2. To use this sheet, there are a few things which need specifying. First, we want to select what data to include. This sheet may use either both ACI and light curve or either of those. Then we may select a calibration to calculate JATP. This is the Yin, the Valentini, the Bellasio calibration, or we may use the fitted values derived in sheet 8-9. Note that the fitted values are available only for the light curve. We may then specify what respiration in the light to use, and then a number of parameters which are generally taken from the literature. Then we may select whether to log transform residuals. To find the value for GBS, we may use Solver, set the objective cell R8 and the variable cell is R7, and then a few constraints are specified to speed up the fitting process. We may now solve, and this value of GBS is the one which fits the selected data. Sheet 11A fits a mechanistic model of C4 photosynthesis to the initial part of the ACI curve. Here are copied those data points which were assigned the limitation 1 and 2. A few things need to be specified. First, what respiration in the light to use. Then, a few parameters taken from the literature, then we may specify whether to log transform residuals. Data from the initial part of the ACI curve are automatically copied here. This sheet can be used in many ways. Here, for instance, GBS is copied from the previous sheet, sheet 10, but a value for GBS may be specified in the formula bar. For instance, we can specify another value, or if the link is to be restored, we may select equals GBS. Both the value of VP max and KP may be fitted, or to increase constraint, we can specify a value for KP taken from the literature. Here is specified 80, and we can only fit VP max. So we may open solver, set the objective cell Q10, which is the sum of the square of the residuals, and then add as a variable cells VP max only, and then we may solve. So now this value represents VP max under ambient oxygen. Sheet 11B is identical to sheet 11A, apart from the fact that here we are fitting the initial part of the ACI curve derived under low oxygen. The oxygen concentration is specified here. We may use the value of respiration in the light derived under low oxygen. We may open solver, select the objective cell as cell Q10, and select the variable cell as cell Q7. We may now solve. This value of VP max now represents the initial part of the ACI curve measured under low oxygen. The two values of VP max derived under low oxygen and derived under ambient oxygen differ. In this case, VP max under low oxygen is 79 and VP max under ambient oxygen is 89. But there is no reason why these values should be different. So we can fit a single value under the assumption that VP max is not influenced by the oxygen concentration. This is an additional constraint which allows us to refine the quality of the estimate for VP max. To do so, we may unhide the additional features in sheet 11B. We now need to modify sheets 11A and 11B to be both linked together. So in cell Q7, we may type equals VP max ambient VP max low. In sheet 11B, in cell Q7, we may type the same formula equals VP max ambient VP max low. Now the two sheets are linked, and in particular they are linked to this value of VP max ambient VP max low in cell AM14. So to find a value of VP max, which will concurrently fit the two curves, we may open Solver, set the objective cell AM13, and set the variable cell VP max ambient, VP max low in cell AM14. We may now click Solve. So this value here now is the value of VP max, which concurrently fits the two ACI curves. The result is plotted in the original two graphs. So we can see the result here in sheet 11B and here in sheet 11A. Another additional feature displayed in sheet 11A and B is a modeled ACI curve. This may be useful to see how the mechanistic ACI curve looks like, because in the main graph only a few points are displayed. Sheet 1213 calculates the final quantities of the C4 model using the parameters we previously derived. There are a few things which need to be specified. Here, as we have seen already, the calibration used to calculate JATP, which may be Yin, Valentini, Bellazio, or the fitted values. Note that the fitted values are available only for the light curve. We may specify what respiration in the light to use. Here in cell J4, it is requested to specify what type of calculation to use. This is two different logic. One uses a mass balance approach, and another logic uses Rubisco specificity approach. Whether to select one or the other may depend on the structure of the error in the dataset and the purpose of the analysis. The value for ATP per GA under low oxygen may be specified together with some other parameters from the literature. GBS is automatically copied from sheet 10, but if preferred, another value can be specified in the formula bar. The calculation is completely automatic, so no action needs to be taken here. We may just have a look at what quantities are derived. JATP, the ATP production rate, VP, which is PEP carboxylation rate, VO, which is Rubisco rate of oxygenation, VC, which is Rubisco rate of carboxylation, VO over VC, F, which is the photorespiration rate, Cm, which is the CO2 concentration in the mesophyll, CBS, the CO2 concentration in the bundle sheet, OBS, the oxygen concentration in the bundle sheet, L, the leak rate, and phi, which is leakiness, which is L over Vp. D is generally valid when light is limited. So those data points which were assigned a limitation which is not light limitation, so all data points which were classified as enzyme limited, in this case assigned the limitation 1 and 2, are highlighted in red. The Bellazio calibration may yield reasonably realistic results also in the enzyme limitation area, but these values should be taken with extreme care. To help the comparison and to help understand whether these values are realistic or not. The C4 model is calculated also in additional features. Here we have the same quantities calculated with the enzyme limited equations. Similar parameters are specified, and here the values highlighted in red are those which were assigned light limitation. So this includes the whole light curve and the light limited part of the ACI curve. Thank you for watching the demonstration. I hope it was useful. If you have any additional questions, just drop an email at c.bellasio@sheffield.ac.uk.